So, for long time, scientists were arguing what is light. What is light? And that discussion actually pushed the development of physics a lot, trying to find what is light. There were two main theories explaining what the light is. One was Newton's theory that the light is a beam of particles, like special particles. And there was another theory that was developed by another physicist, Huygens, who was saying that the light is a wave. And at the time, when there were like two competing models, light wave or light particle, because Newton was so much respected, so big name by many, considered the biggest name in the history of the science. And Newton's point of view was pretty much dominated. Until one experiment, which we will learn later on today, which completely proved that the light is a wave. And then everyone knew that light is a wave. Until another experiment that we will learn later on today happened, which showed that the light is particles. So when you say what is light, it's a dual nature. It is a wave and it is a beam of particles. Like one of the physicists, and I forgot his name, who said that, where I like this phrase that on Monday, Wednesday and Friday, light behaved as a wave. On Tuesday, Thursday and Saturday, it behaved like a particle. What it does on Sunday, nobody knows. And so it has both properties, waves and particles. And later on we will learn that particles like electrons, protons, they behave not only as a particle, they can behave as a waves. And we will learn that wave behavior of electrons actually determine those shells, so-called shells in the atoms, what we're talking in chemistry about. That's all from the wave properties of the particles. But that's later on. So today we're focusing on the wave properties of light. And what how Huygens explained the wave propagation. Let's have it. Now, according to Huygens' theory, the light was propagated. So let's consider if we're starting the Huygens, so-called Huygens principle. How we start a wave? If you just drop a stone into the water, it creates the wave going around. But what if we drop instead of just one stone? We drop few stones. Then the waves created by each stone, they will superimpose on each other. Each stone, when it's dropped, creates the circular wave coming around in all directions. And when they all adds up, what we see actually the straight wave front coming that way. As you can see, this straight wave front. This is a result of addition of many these circular waves created by the point of the where the wave is created. Now, if we have on the way of the wave, we have some obstacles. And we can see, and you've seen probably on the water, that wave can go around those obstacles. How it happens? So when wave came here, and each point in this opening becomes a source of the point source of the wave. And those waves, they going in all directions from each point. And what we see is the result of the addition of these many circular waves. So that's wave going around the obstacles. This property of the waves to go around the obstacles called diffraction. This ability of the waves go around the obstacle are called diffraction. Can you give me an example with the diffraction of a sound, for example?
Like people outside will be able to hear if they're around the corner. When
Yeah, if someone's saying something around the corner, you can hear it. The wave not going straight through the corner of the building, but waves can go around. So that's pretty much same thing. And as you can see, those lines represent peaks of the wave, those represent troughs of the wave. So that is the Huygens principle, how it works. Let's see how it can work with the light. Even if we have, they removed reflection, refraction of the light from the curriculum again, bring to unit 1. So if we have when we have the light coming and it's reflecting, how we can see. We have a light coming. Each point here become a source. When light comes, they become a source of the wave. And that's how the wave is created, the reflected wave. So it's all becoming as a superposition of the wave coming from each individual point of the wave. Now, we were talking about the diffraction, the ability of the wave to go around the obstacles. So let's have a look more into the diffraction. So we'll put a slit. Let's see. So we have the wave just so as you can see, we have a wave coming and there is an obstacle, there is a small opening through which waves can come. And as you can see, waves coming around because each point in the opening becomes a point source of the circular wave. And very interesting thing happens if you will be changing the relationship between wavelengths and the width of the now we can so, as you can see, and we've discussed that the wave can superimpose on each other, that's called interference. The wave can add up and make a bigger wave, or they can cancel each other. If you can see here, in this picture, we have some lines where pretty much nothing happens. You see those lines where waves cancel, and we see there are ways where waves become. Can you see here that here, here that the waves cancel each other. There is a relatively undisturbed, medium. Can you see that, those lines? Now, let's consider look more in detail into the diffraction. What determines the amount of diffraction? Amount of the diffraction, how much light is diffracted, so going around the object, depends on the, if we have this is the slit opening. Let's say its width is doubling. The relation between wavelengths of the wave, and we're talking about the light, and it's not just for the light, but in this case, we're talking about the light, ratio wavelengths to the opening. That determines amount of the diffraction. That determines amount of the diffraction.
So is high diffraction like a lot gets through?
A lot of diffraction when it's going a lot going around. Little diffraction if it's going almost in a straight line, just straight. And we have, if this will be greater than 1, or we'll put greater or equal to 1, there will be a lot of diffraction. The bigger it is, this ratio, the more diffraction. But will we actually be able to observe diffraction? To observe the so-called diffraction pattern with the maximums and minimums? It all depends. If we have this will be greater than 10 approximately, there will be a lot of diffraction. But we will not see any diffraction pattern with the maximums and minimums. As we see the lines, when you see the lines with the maximums of the wave and the places where there is no wave, the wave cancel each other, we will not observe this picture. There will be a lot of diffraction, but we will not see this. The best when we can see the observed diffraction when this equals to 1. When this ratio equals to 1, will be good diffraction and we'll get a good picture. We can see the pattern. In this case, there is a diffraction, like wave going around the obstacle. But as we don't see diffraction pattern of the maximums and minimums. Point of the constructive, destructive interference. And we still see diffraction up to, so if this is greater than 1/10, we still see diffraction.
So between one
So between when this ratio is between 0.1 and 10, we will see diffraction. We will see diffraction. When it's greater, becomes bigger, there is a diffraction, but we will not see the pattern. When that is greater than this, there will be very little or almost no diffraction happens. When it's equal 1, we will see the best diffraction. We will see diffraction happens, and we see those lines of minimum and maximum. That's why, for example, sound, if you talk diffraction of the sound, we talk that sound can go around the corner. If you will have music playing here, and sound will be listening to it straight through the opening door, that person will hear music exactly as it played. But if you will stay to the side, will be music sounds the same. I'm not talking about the loudness. I'm talking about the actual music, the frequency. Which frequency will diffract more? Low frequency or higher frequency?
Low.
Low frequency will diffract more. Why?
Did you say when the ratio is bigger? Did you say when the ratio is bigger, it diffracts more?
Yes. So low frequency wavelengths longer. When we have frequency decreases, wavelengths increases. So we'll have more diffraction. So low frequency, long wavelengths will easily go around through the door and around, and you can hear low frequency. You can hear sound with a low pitch. But high frequency sound will not diffract because it has high frequency and so small wavelengths. And so, because this would determine the amount of diffraction, short wave, small wavelength, short wavelengths, no diffraction. So high frequency will not go to the side. So person listening to music like around the corner will hear it distorted. Will hear low frequency but not high frequency. Make sense? And now we come to that experiment, and famous one of the big experiments in the history of physics, which determined that the light is a wave. We're talking about the Young's double slit experiment. Young's double slit experiment. If we have what he did, one, he had a source of light, then he has one narrow slit, then he has two other slits here. And that was the screen. And when the light, so those opening S1, slit 1, slit 2, they were acting like sources of light, point sources of light. And on the screen, he observed interference pattern. So interference pattern is the pattern where we have we see maximums and minimums. Light produced, because if light will be a beam of particle, what we will expect to see on the screen? No, if we have two sources of light, we'll have just two bright bands, one here, one here. But he observed many bright bands, bright, dark, bright, dark, bright, dark, in both directions. And that cannot be explained by the particle model of light. Because what we observe is interference, addition of waves. So interference as a result of diffraction, and those are exclusively wave properties. Particles does not have interference. Two particles cannot be at the same time in the same place. One takes this place, another cannot get there. So we have seen this interference pattern. Young's showed that the light is a wave. Why it was important to have it from the one source? If you take two independent sources of light, even with the same frequency, you will not obtain stable interference pattern. Because for light to see this interference pattern, light has to be coherent. What does it mean, coherent light? First, it's the same wavelengths. Wavelengths of frequency. But also they must be in phase. So they start when we have from here coming crest coming from here. Trough from here, trough from here. they synchronized. That light called coherent. When it has the same wavelength and so frequency and it's in phase. Those lights are coherent because they come from the same light, from same source. So when we have here minimum, here minimum, if they will not be synchronized, those two lights, they still will be adding, but it will be all the time changing where we have maximum, where we have minimum. We will not see the stable picture. Make sense? Yes.
Wouldn't it still work without the single slit one on the left?
Yes, it could. It could, just how he did it to make it like more narrow slit, narrow beam of light. Yeah. Now let's see what happens. How this interference pattern of the dark and bright bands is formed. How it is formed. So we have two slits, those two slits. This is the screen, and we have light from one slit.
It's unplugged.
So one light, another light coming. Let's see how what we will observe on the screen. It's not like the lights coming like this. We just showing it's all happens simultaneously at the same time. But at the some points of the screen, we will see the bright bands of light. At some points, we will see dark bands. What determines that? If we will get first to the central band, so this band, bright band, is exactly opposite to the midpoint between two sources of light. And so the light came same distance from one source and from another source. If they came same distance, because what determines what we will observe on the screen depends on the path difference. Path difference. So difference between distances, how far one light has to travel compared to another. When there is a path, what the path difference here in the center? 0. When the path difference, there is no special letter, you just write PD, path difference, equals 0 in the center. And both came in phase. They came in phase here. And it always adds up. The light maximum from one came at the same time with the maximum of another. Minimum one came at the same time with another. Yes? Path difference is a difference. So we have, this is point on the screen, let's say P. This is S1, source 1 or slit 1, S2. And path difference equal S1P minus S2P. It's the difference in the distance that light traveled to the point on the screen. Difference in the path. In the center, in the middle, it came same distance. Now let's see when we go to another point. Here, there is a difference. From S1, light have to travel more. From S1 to this point on the screen, as you can see, S1 S1, S2. They are not equal now. But what is difference? What do you think should be different S1P minus S2P? This is the path difference. Light from S1 travels more, bigger distance. What should be that path difference? And path difference we can, if you draw the perpendicular from this here, that will be, it's not very well. So if you draw the perpendicular, that will be path difference. This bit is the path difference. How much more light from this source have to travel compared to this. To have them here again in phase, what should be the path difference? One what?
Can just be n, like n wavelengths.
One way.
Has to be one wavelength for the first one. It will be one wavelength. If we take wave and we shift it by one wavelength, we'll get exactly the same wave. So, if path difference to here is one wavelength, path difference to here will be two wavelengths. To the next maybe will be three wavelengths. So, generally we can say when the path difference when we have path difference equal, as you correctly say, n times wavelengths, where n is natural number, is 0, 1, 2, 3, so natural number and 0, we will have maximum. We have constructive path difference equal whole number of the wavelengths. We have constructive interference. They came in phase. One wave came and second wave came. If you shift them by the whole number of the wavelengths, they will come in phase. To be minimum, to light cancel each other, to waves cancel each other, to adds up and give us, in this case, dark band. So light can cancel each other. Two lights meet and we got darkness. How the waves need to meet? If this is one, then another has to be other way around, where we had peak of one, crest of one, meet with the trough of another. What should be then path difference to have? It's called destructive interference.
0.5.
Yes, you're right. So we have minimum. The path difference has to be half wavelength. Does that make sense? That if there will be difference half wavelengths, then we have crest, mid, trough, and they cancel each other. What will be the condition for next minimum?
On 4.
3,
2.
3 on 2. 3 wavelengths on 2. 5 wavelengths on 2, and so on. How we can express this with the one mathematical formula?
and wavelength on 2.
2n minus 1 on 2 times wavelengths. That will give us odd number. 2n minus 1 on 2 times wavelengths. This, if the path difference equals that, we will get destructive interference, and there will be dark band. If path difference equals this, we will get constructive interference and bright band. So obtaining this pattern of the bright and dark bands on the screen, Young proved 100% that the light is a wave, because interference is exclusively wave features. So I'll sketch this pattern. So we have sources, we have screen here, and on the screen we have in the middle we always have bright. And path difference equals 0. Here we have path difference equal half wavelength. Here again half wavelength. Then we have another bright band to each. Then we have path difference equal 1 wavelength. 1 wavelength. Then we have another dark band. The path difference here will be 3 wavelengths on 2. Dark band 3 wavelengths on 2. Then we have bright band 2 wavelengths. We have path difference 2 wavelengths. Remember, it's a path difference. It's a difference in the distance that light travels from one source and another. How far more one wave has to travel. That's what we will see. Dark and bright bands. And what determines how much they will be separated on the screen. Let's say this distance is L, distance to the screen is capital L, lambda is the wavelength, and we also will have D split separations. And delta X is a separation of the band. So distance from one bright band to another, or dark band to another. So this is delta X, separation of the bands. How it will be changing with the wavelengths? What do you think? If we will increase wavelengths, what will happen if wavelength becomes bigger? We will have more diffraction or less diffraction? Longer wavelengths? More diffraction. So light spreads out more.
So it'll be bigger.
So it will be bigger. So what we've got, the formula that described it, delta X is separation of the bands on the screen. Distance, let's say, from the center of one bright band to next bright band, or from one dark band to the center to the, another dark band. And it will be proportional to wavelengths, distance to the screen, and inversely proportional to the slit separations. This is delta X is this distance between from one bright to another bright on the screen. L is a distance to the screen, from the slits to the screen. D is how far those two slits from each other, how they are separated. So, if we will be, let's say, for which light we will get wider pattern, for a red or blue?
Red.
Red has longer wavelengths, so if we have a red light, the pattern spreads out. Blue shrinks. What will happen if we will start move slits closer together? What will happen with the pattern?
Spread apart.
It will spread apart. If we make the denominator smaller, what will happen with the delta X? Increases. So, or if you move them further away, the picture, the interference pattern will shrink. So this is formula describing us relation between the separation of the bands, separation of the slits, and distance to the screen. And it's almost certainly on the exam will be questioned based on this formula. Like 90% that it's on most of the exam there will be, and there will be questions about this, and we'll start practicing from the next lesson. Like, subscribe, and donate to help fight the terrorist countries and organizations like Russia, Hamas, support Ukraine and Israel.